And then we're going to practice. We're just going to get ready for the exam. Practice, 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 and then we'll be ready. We're going to start with an opening prayer by our wonderful PA, Sam.
Our dear Father, we're grateful to be gathered here at thy university, and we're grateful for all the things that thou hast revealed to us and to help us come unto thee. Father, please bless us as we try to understand physics, that thou will bless us with inspiration. We're grateful for thy servant Greg and how good he has been to all of us. And these things we ask in the name of Jesus Christ. Amen.
Thanks. Okay. So let's talk about some announcements. As you know, we always put the homework solutions up at the Mac site. I encourage you to go and look over those and see that you not only got the right answer, but also understand the right reasoning, that you just didn't follow along with the group in the help center. There's an exam preparation sheet at Max, but I also handed you a hard copy of that. The 2 practice exams and their solutions are there. I hope that everyone got the email from Dr. Benyon showing you how to go to that online sample exam. Just like last time, this is meant more to test your preparation, not so much to teach you. That's what these 2 paper exams are for, to let you try the problems and look at the solutions and see how to solve those problems. On the online, Dr. Benyon's not going to give you the answer so that you can take it again, the next day, and you can just keep on trying to get better and better without looking at a solution key. There's a review session tomorrow evening right here at 7 o'clock. I will record that and post it at YouTube and send you out a link to that. Regarding that midterm, and I'm embarrassed to say this, but after that last midterm, I was exhausted. I mean, it took forever to grade 860, no, I was exaggerating, 665 exams. And then we really had a hard time getting it back to you. And part of that was because a lot of our TAs had to leave before the exams got completely graded. And so, it was Sam and I and 4 others that were there until late at night getting that done. And then we entered it into the computer, but we weren't the ones that were going to hand it back to you in tutorial. And so it got all messy. And so this exam is just going to be multiple choice, and you don't write on the exam. You write on the bubble sheet, and after you walk out, they'll tell you how you did, but they won't tell you which questions you missed until after everyone's taken the exam, after Tuesday closes the exam. What that means is you need to bring scratch paper, because you can't just be scribbling all over that exam. Again, as I've said many times before, not all of the equations will be given on the front page of that exam. And that's because I love you, okay? You need to know what kinetic energy is, 1/2 mv squared. You need to know what gravitational potential energy is, mgh. You need to know what spring potential energy is, 1/2 k delta S squared. You need to know what Verk is. You also need to know what impulse is. Those definitions will not be on the front page of the exam, because you're going to be better people. You're going to understand the problems much better if you recognize those players on the field. Okay? Are there questions about this midterm that haven't been covered?
I'm still.
It's going to be fun. Okay. Well, folks, again, you have my cell phone number. Okay. If you have questions, if you get stuck, if you need someone to get things clarified, just give me a holler. Okay. Let's talk about power now. Suppose I were to tell you that Greg can do 5 billion joules of work, of work. Question, is Greg a powerful man? Before you answer, remember we've got that exam coming up, okay? What question would you like to ask?
How powerful.
Yeah, how long does it take? Is this gonna take a minute or is this gonna take the rest of his life, 5 years? Okay? Oh, oh, that's dark? Sorry. As you get older, you just get more realistic. Okay. I've been to a lot of funerals of my friends. So, okay, power is just how much work Greg can do in 1 unit of time. And we typically take that unit to be 1 second. How much work Greg can do in 1 second. Now, that's the operational definition. Remember, anytime you have a definition that is a ratio, something divided by something else, the best way to understand what that is at a gut level is to make the basement 1. Set the basement equal to 1 second, and that'll tell you what we mean by power. How much work you can do in 1 second. Now, because work or work is what changes total mechanical energy, I can also write the equation this way. If I know how much the energy of the system changed, I just divide that by how many seconds it took to make that change. Now, there's a special case, and that's the case when something is moving at a constant velocity with a constant push. Now, you know that a constant push on a frictionless table is going to speed things up, okay? So clearly, there has to be friction involved. And if I only want to know the power delivered by my hand, I don't care about the power due to the friction. I can just use that force by the hand and the distance traveled divided by the distance, the time involved. Well, the distance traveled divided by the time is the speed, the velocity. And so that formula there is another way of calculating power. The force times the speed. Now, this is only valid if the force and the V are constant. If I'm always pushing with 50 newtons and it's traveling at 3 meters per second, I just take the 50 newtons multiplied by the 3 meters per second.
Has magnitude direction?
Power does not have magnitude and direction. It has, because it is like energy, change in energy, remember, is like changing your bank account. It can either be positive or negative, but that has nothing to do with the direction. It has everything to do with whether the bucket is filling or draining. And so if you're doing positive work on a system, you're delivering positive power. If you're slowing something down like the friction force, you're bleeding energy out of the system, we would say that's negative power. But it's not, and I apologize that the negative sign can mean so many different things. But it was that way before I was born. Okay, it's not my fault. Okay, when we're talking about vector quantities, it means right or left or up and down. When we're talking about the change in something like energy, we mean, is it growing or draining? And that's what we have here. Power is not a vector. It is just like the change in energy. Now, what units do we use for power? Does anyone know? Power is measured in, yes,
Velocity. Velocity.
there was someone over here. Watts or kilowatts, okay? A watt is just a joule for each second. A joule for each second. A watt. And again, it's named after a dead professor. How many of you, by show of hands, pay your own power bill? Oh, okay, that's fun, isn't it? Yeah. When you pay your power bill from the power company, what is it you're actually buying from the power company? When you open that power bill and you write the check to the power company, what are you buying from them? Power? It would seem. Otherwise, they'd need a different name, wouldn't they? What do they actually charge you for when you get your bill and you open it up? How many, your electric bill? Yeah, kilowatt hours. And if we look at a kilowatt hour, well, a kilowatt is just 1,000 watts or 1,000 joules each second. And an hour, if you'll believe it, is only 3,600 seconds. It seems longer in a physics class, but that's what it is. It's 3,600 seconds. And if I multiply those together, what I get is 1,000 joules per second times 3,600 seconds. The seconds cancel out and I get 3,600,000 joules. Energy. What we buy from the energy company, it should be called the energy company, is energy. Now, when I was young, I thought we also bought electrons. I thought that when you plug something in, electrons came rushing out of the wall, or maybe they went rushing into the wall. I didn't know. And I thought that these electrons were rushing through my wires at the speed of light. Well, that just ain't so, okay? When you flip the switch, the message goes out at the speed of light, light the bulb, okay? And all the electrons start marching. It's like the electrons are a bunch of soldiers in a line. And when you flip the switch, the command goes out at the speed of light, 10 hook, forward march, and then they start marching. But the speed at which they march is terribly, terribly slow. We're talking centimeters per minute, okay? And you know, if you look at the starter motor in your car and you follow one electron, you paint him green and call him Fred, and you turn the key in your car and you just leave the key on and you watch Fred go from one terminal of the battery through your starter engine and back to the other terminal of the battery. It takes 2 weeks for Fred to get back. It's that slow. Now, it's complicated by the fact that in your house, we have what's called AC power, alternating current. That means that 60 times a second, we change the direction of that current, okay? Actually 120 times, it's 60 hertz, but it's 120 times a second, they change direction. And if you use the fact that these electrons aren't traveling very fast in the wires, what you're buying from the power company is for them to come in and just shake the electrons in your lamp, okay? Because they don't get very far before they turn around and go back the other way. They're just vibrating back and forth, and that makes the filament in the lamp hot. It glows, and we have light, okay? That's not going to be on the exam, folks, but this might, okay? That's a lot of energy. Remember when we had two great big Volvos going 60 miles an hour, that was enough energy, capacity to do damage, it was 1,000,000 joules. Well, this is 3 times that much. Well, that's a lot of energy. That could do a lot of damage. And yet this is the amount of energy that would light a 100-watt bulb for 10 hours. And you would have to pay in Utah 13 cents for that. What I'm saying is that electric energy is dirt cheap. No, I'm not saying that you should waste it. I'm not saying you should leave all the lights on, but I'm saying you should not ruin your marriage over it, okay? If your spouse or your children leave a light on, just love them, okay? It's not a big deal. I'm sorry, I'm gonna, story time. 32 years ago when we moved to Montana, we were the new shiny thing and people were inviting us to their homes, and we got invited to this member of the ward that was a doctor, very rich, a big mansion. And we were at his home with a bunch of other people, and all night long he was just ragging on his poor wife. She was, oh man, she just wastes money, wastes money, wastes money. And then he was telling a story about he came home from his hunting trip in his great big huge truck with all of his very expensive equipment, and every light in the mansion was on. And when he finally got to the pulled into the driveway, she was out on the porch, turned on that light. And finally I'd had enough, and I said, JD, if she leaves all the lights on for the whole month, you're going to spend an extra 20 bucks. I took my daughter to you to have a wart burned off of her foot, and I had to pay 150 bucks. If you want to save money, just don't go to you. We were never invited back. I don't understand that. And then I was called to serve in a branch 90 miles away. Who saw that coming? Okay. That's not going to be on the test. Many years ago, when I was just fresh out of grad school, I went to work at Lawrence Livermore National Laboratory, one of our nation's top secret laboratories. And at that laboratory, they had the most powerful laser in the world, and that's a Nova laser. And to this day, it is still the most powerful laser in the world. And this laser actually has 10 beams, and it's in a building that's about the length of a football field. And see, these are the 10 beam lines. That right there is a scientist. They're a little bit smaller than humans, but not that much. So you can see the scale of this. And as these laser beams, there's 10 of them, go down these beam lines, we continually drop through a quantum process energy into the beam. And so by the time they get to the target, and this is the target, they're very powerful. And again, those are the scientists there, so you can see the scale of things. Now, in the very center of that target chamber, we have a target which is tiny. It's just this little tiny glass bead that contains deuterium and tritium, heavy hydrogen. Okay, and then that is essentially bombarded on from 10 different directions to create the same density and temperature that you have in the center of the sun. And we do that in order to create the same process that powers the sun. Namely, we take the deuterium and tritium, and with all that pressure and temperature, fuse those nuclei together to create a helium nucleus and a neutron and a whole bunch of energy. Well, how much energy? Well, if you take 1 gallon of seawater, extract the deuterium and tritium, the heavy hydrogen, you still have pretty much all of the seawater left to surf on, okay? But in the process, we create the same energy as 600 barrels of oil. This is amazing. If we can get this to work, it's free energy for everybody. It changes the world. Now, when I was at Lawrence Livermore National Laboratories working on this problem, we were telling our friends and family that we were 20 years away. And that was 1987. My friends who are still working on this problem tell me that they are only 20 years away from solving it. So we're just around the corner, folks. Just around the corner. Now, the reason I bring this up is that this Nova laser delivers 200 times the total power output of all the power stations in the United States. Of all the power stations in the United States combined. Where's that power coming from? Canada? Mexico? I mean, where? It's coming from math. Coming from math. You see, that definition of power has a basement. And whenever you have a definition that has a basement, there's two ways to make that big. One way is to just deliver an enormous amount of energy in a reasonable amount of time. But that's not the way the Nova laser works. What they do is they deliver a reasonable amount of energy in less than a billionth of a second, in a very, very short amount of time. Now, the power station that brings electricity to your house has to deliver that energy 24/7. Otherwise, you can't cook your food, okay? They only have to deliver this energy for less than a billionth of a second once every afternoon. What they do is in the basement of this great big enormous cavernous building the size of a football field, there's an enormous basement room filled with capacitors that we're going to learn about next semester in 106. Capacitors just hold electrical energy and charge. And they trickle that energy into that capacitor bank all day for 24 hours until they're all charged up. And then they dump all that energy again in less than a billionth of a second into the game. Now, let's talk about 106. How many of you are taking 106 next semester? Yeah, you think. I found out yesterday that every seat in the 106 class, both sections, is already filled. The other physics classes in the department, you know, half filled, third filled. Our class is completely filled, and there are 180 people wanting to get in. And so I'm working with the department to open up a third section so that we can get everyone in, because like you need it to become doctors, right? Yeah, okay. So I will keep you posted on that, but it looks like they are willing to make some accommodations to get everybody in. Okay. So what I'm saying is, please don't be asking me for ad codes yet. Let's get the room reserved so that we can put you into it before I start handing out ad codes.
Are you still thinking Tuesday, Thursday schedule for this third section?
Yes, it will be a Tuesday, Thursday schedule, and all of the tutorials in that class happen on Wednesday. So there is a Monday, Wednesday, Friday version of 106. Unfortunately, it also involves getting on the front runner and going up to Salt Lake. And from what I understand, all of the students in that class ride the front runner up together, take the class together, and then ride the front runner back because they're all from Provo. So it doesn't make a whole lot of sense to me, but I'm new here. Okay, other questions on this? Let's see if we understand it. Here's a sample exam question. A box is pushed by a hand across a level table at constant speed. That tells you there has to be a friction force involved, right? Otherwise, it would be speeding up. The frictional force exerted by the table on the box is 20 newtons. The box moves a distance of 12 meters every 3 seconds. What is the power being supplied by the hand? And I'm going to get you started right now. Okay. Now you can click. Okay.
No, I haven't.
Okay, last call. Get your attendance points.
I really do. That's a good will.
Okay. D, 80, 80 is the correct answer. Good job. So, how did you get that? Well, we know that if it's moving at a constant velocity, constant speed in a straight line, that's zero acceleration. And that means that the force by the hand must equal the force by the friction, or 20 newtons. If I use that definition of power in terms of Werk divided by the time, and I use the definition of Werk to get that as force times the distance, well, that's just going to be force times the speed, since we're dividing by the time. And so the force is 20 newtons. It travels 12 meters in 3 seconds. That's a speed of 4 meters per second. 20 times 4, 80 watts. Yes, sir.
80 watts, but friction is like, if we're calculating, like, it's technically, it's.
Yes. Yes, yes, yes.
Don't we?
And the key here is the words by the hand. So if I had asked for the Werk done by the friction on the block, that would be a negative 80 watts. Okay, because it's bleeding energy out of the system. But the hand is pushing in the same direction it's going. The hand is doing positive Werk as time goes on. So the hand's doing a positive 80 watts. The friction would be doing a negative 80 watts. And remember, power is the energy going in or out each second. If I'm putting in the same amount each second that the friction is taking out each second, the total energy of that block is not changing. And that's kind of what it feels like when it's just moving across the table at constant velocity. Its kinetic energy isn't changing. Gravitational energy isn't changing. There's no springs.
Or the masters.
No, because that F there is not the force by the friction. It's the force by the hand, because I'm looking for the power delivered by the hand. And so it would be a positive F. If I were looking for the work done by the friction, it would be a minus. Okay, other questions on that? Let's try another one. How many joules of work can a 15,000 watt motor do in 20 minutes? Again, let me get you started. Okay, now you can click.
Is equal to 30,000.
There's way more seconds. You got wrong direction.
How many?
Keep trying to click it. I never said.
Okay. Get your vote in. If you haven't clicked yet, just take a stab at the dart. Don't miss out on those points. Okay, I'm closing it up. Good. Okay, folks, I deliberately put this problem in to address a test strategy. There are some questions that you don't need your calculator for if you understand the concepts. This 15,000 watt motor can do 15,000 joules of Verk in 1 second. In 1 second. To do what I'm saying is that those first three answers are silly, right? They're all the amount of work much, much less than what it could do in 1 second, let alone 20 minutes. And this answer here, that's how much work this motor could do in 2 seconds. Well, 20 minutes is more than 2 seconds, right? This is the only answer that makes any sense whatsoever. You don't need the calculator. Now, having said that, most of the problems on that exam are going to need the calculator. They're going to need you to treat them as if they were long answer questions. I wrote the test last week. I wrote the solution key yesterday. And I couldn't remember what the answers were. I couldn't just go and circle the answers. I had to take out paper and work the problems again. And I filled up, 4 pages front and back with all the math to get those answers. So don't expect all of the problems to be like this. Don't expect that you can look at these problems and just sniff the air and say, oh yeah, that's D. No, not so. Okay, you're gonna have to reason it out.
Scratch paper.
You have to turn in your scratch paper and then they throw it away. Does anyone know the answer to this? I'm again new here. Do they give you your scratch paper back or they don't? So I will make a video going over the problems after the test is over. And okay. Again, this is the first time I've ever done a test this way, so. Let's turn our attention now to a long answer problem. And Sam, would you give me a hand handing these out? Sure.
Like, how the heck is that going down?
Bryson, I'm sorry. I got it so bad.
What's the student? That's probably like.
Sam, can I have some of yours? Yeah.
Like, oh.
So this is the last payment. Where's it? No. It's so true.
Coming down.
Everything and I could not be
That string is not only frictionless, but massless.
Solitaire.
Okay, people, raise your hand if you still need one. Sorry about that. Anyone else over here? Oh, yes.
6% back on dirt. 3% back on
These people back here need some.
only pay 94%.
You need some? Okay, let's look at this power problem. How many? Plethora? Okay,
Yeah, I already. One.
everyone has one now? Okay. Let's look at this problem. We have a block of dry ice floating on a layer of gas because it sublimes down this ramp. So there's no friction acting on the ice. But it's got an anchor that it's dragging, that brick. And because of that anchor, it's traveling at a constant 5 meters per second down the incline. And so the first thing we're asked to do in that problem is find the tension in the string. And the question back there was whether this was a massless string, but of course it is. Because that's how we roll. Okay. Now, we're asked to find a force, the tension force. That should trigger in you a reaction. You should start twitching and immediately know what to do. When you're looking for a force, what's the first step? Free body diagram. Free body diagram of what? Everything in the problem that has mass. Not the string, but everything that has mass. So let's start with the ice. I first of all put the gravitational force, Earth on the ice. And then I asked, are there any magnets in this problem? No. So what touches the ice? Well, two things, the string and the ramp. Well, the string pulls up the ramp with a tension force on the ice. And the ramp pushes with a normal force, but no friction. And that's the free body diagram. I know I'm finished because I followed the recipe. Now, if I draw the free body diagram for the brick, I have a smaller weight force. And then I asked any magnets, no. So what touches the brick? Well, again, it's just a string and the ramp. Well, the string pulls down the ramp. The normal force is perpendicular to the ramp. And then I've got a friction force. I can hear the scraping going on. And so that's going to be kinetic friction. Now, whenever I have a ramp or a hill, I always rotate my coordinate system to line up with the ramp or hill. And that means all of my forces are going to be lined up pretty much with the coordinate system, except for the weight. It's always the weight. And I break that up by always doing the same thing. I look in the direction of the normal force, and I go the other way until I can make a 90-degree turn and get to the end of that weight force. If I do that, this angle here is going to be the same as the angle of the ramp, 37 degrees. And then, since I know that this is 300 newtons, I can use my trig to find out these parts. This would be the y part of the weight. That's going to be 300 newtons times the cosine of 37 degrees. And that's going to be 240 newtons. This x part of the weight is going to be 300 newtons times the sine of 37 degrees. And that's going to be 180 newtons. Now, once I've broken the weight up into its parts, I throw away the original and I use the parts. Now, the important thing about the velocity is that it stays constant. That should ring bells in our head that say zero acceleration. So zero acceleration tells me that my diagram had better scream zero, which means I drew this too long, okay? If the x part of the weight down the ramp is 180, this tension up the ramp must be 180. In the y direction, I have one force in the positive y direction, one in the negative y direction. This must also be 240 newtons. Okay, is that all coming back? That seems like old news. So we were able to find the tension force, part A, based on just the free body diagram for the ice. Now, part B asks us for the power delivered by the string. Be careful with your reading skills. By the string to the brick. Well, that's this force here. Okay, and we know by the law of massless strings that this must also be 180 newtons. And because that force on the brick is pulling on the brick in the same direction the brick is moving, what? Positive or negative, Eric, being done? Positive, okay, positive. And so that means for part B, the power delivered by the string to the brick is going to be the tension force times the speed. So that's going to be 180 newtons times 5 meters per second. That's going to give me 900 watts. Now again, that's going to be a positive 900 watts because the string is doing positive work on that brick, pulling in the same direction that it's going. At the end of this problem, we're going to find the power delivered by the string to the ice, and we're going to find that it's a negative 900 watts because the string is pulling this way on the ice while the ice is moving that way. And you remember that Werk had that messy definition. It's positive force times the distance if those are in the same direction. It's negative force times the distance if those are in opposite direction. And it's 0 if they're perpendicular. Check that your neighbor's on the bus so far.
That's early, 'cause I had-
Okay,
Has to be.
part C asks us to compare this friction force to this tension force. Is the friction force going to be greater than, equal to, or less than the magnitude of the tension in the string? Well, again, we use the coordinate system that lines up with the ramp. We break up the weight force into its parts, same way we always do. And this would be the y part, and this would be the x part. We throw away the original. We remind ourselves that there's no acceleration. And in the x direction, that means all the force down the ramp has to be balanced by all the force up the ramp. And so what that means is that the friction force up the ramp has to balance both the tension force by the string on the brick plus the x part of the weight. So that means the friction has to be bigger than the tension in the string. That makes sense? Now, the next question is a philosophical question. Is the mechanical energy, remember that's the type of energy we have buckets for, we have equations for, is the mechanical energy conserved for, listen carefully, the ice-earth system? By including the earth in our system, we don't have to worry about any work done by the gravitational force. That's all in the gravitational potential energy bucket. But the ramp's not in the system. The friction force is not in the system. The string is not in the system. Okay? So when we answer this question, the best way to do it is to just look at what we mean by mechanical energy. That's going to be the kinetic energy plus the gravitational energy plus any spring energy, but there's no springs in this problem. Is this conserved? Does this stay the same? Shout it out. Yeah, it's always going the same speed, 1/2 mv squared, it's always the same. What about this? Is this conserved? Shout it out. No or heck no? Yeah, it's getting closer to the center of the earth. The earth and the block are getting closer to each other. That's not conserved. And so if this is getting smaller, and this is staying the same, the total mechanical energy is getting smaller. Now, what that means is that we're being robbed. Something's bleeding energy out of the system. Well, we find in the last part that the string is bleeding 900 joules away from the ice every second that goes by. But it's delivering those 900 joules to the brick every second that ticks by. So the string isn't really taking energy out from the combined system of the brick and the ice. But that's not the system we were asked about, was it? We were asked about the ice earth system. And since the string is doing negative, Eric, on it, taking away 900 joules every second, that's why the total mechanical energy of the ice earth system is getting smaller. Check with your neighbor, see if your neighbor is still understanding.
What I was thinking, your system's nice. Okay.
Yeah.
If the energy is staying,
Okay,
have to go up. Have to accelerate, but since it's already accelerating.
So that.
we can practice the ideas that we've covered thus far in the class by trying to figure out the different ways that we could measure the muzzle velocity of a bullet from a rifle. There's our rifle, and we're going to fire that bullet out of the rifle. We want to measure how fast it's going. So let's talk about some different ways. We could use a radar detector and do it that way, but that seems dangerous. Let's skip that plan. Although I found this on the internet, some jobs are better than others. You have to trust your friends. We could also use kinematics. If we fire that bullet perfectly horizontal, we know that gravity is going to cause it to go in a parabolic path, projectile motion. And we know that the x part, or the horizontal part of that velocity, if we ignore air resistance, stays the same. So if we can measure how far it goes and measure how much time it takes to go that far, we just divide the distance by the time. But if we didn't want to use our clock, if we didn't want to use our Mickey, we could also use our kinematic equations. If we knew how high the barrel of the gun was above the level ground, we could just use our kinematic equation that relates that displacement to the gravitational acceleration and time. We would solve that for time, and then we would solve this for V. Another way is to use our ideas of energy. If you were working for the FBI and you wanted to measure the muzzle velocity, you might lean your head out the window in your high-rise building that you work in and ask one of your coworkers to run up to the 20th floor, and you would fire the bullet up, and your coworker would, stick their head out to see how high it goes. I'm not recommending this approach either. But if we did that, we could just relate the kinetic energy that the bullet has when it leaves the barrel to the gravitational potential energy that it has when it turns around at the top. And we would set those equal to each other, again, assuming that there's no Werk done by wind resistance, a silly thing to do with a bullet. But if we plug in what we know about those energies, the mass cancels, and we can quickly solve for V. Now, what's more likely to be done is we use the idea of momentum and energy. In other words, we fire the bullet into a block of wood, and then that block of wood scrapes across a rough table until it stops. If I measure the friction force and I measure the distance that it travels, I can figure out how fast the bullet was going. Well, first of all, I look at the collision between the bullet and the block. Do I conserve energy or momentum there? It's a collision. I conserve momentum. And so I would say that the momentum of the system before the collision is equal to the momentum of the system after. Before the collision, the only thing moving is the bullet. Afterwards, the bullet and the block are moving together. And so I have this equation here. There's the bullet. There's the block and the bullet moving at some final velocity. Well, that final velocity is how fast it's going at the beginning of the slide. And so if I want to know the speed of the bullet, I need to find this speed here. Well, I can find that speed by looking at the energy. Well, I start with kinetic energy. That's the bullet and the block moving at this speed. And then I do Verk through the friction force, negative Verk, to bring it to a stop. And if I solve this for this V block, if I solve this for V block, plug it in here, I can solve for V. Now, the last way is a way that is often used, and that's called the ballistic pendulum. And that way we fire the bullet into the block, and then we watch as it swings up and we measure how high it goes. What we do is we conserve momentum here, and then we conserve energy here because a Tarzan swing does no Verk. That makes sense? I went through that a little bit quickly because I'd like to take some time to just review some very important ideas to get you ready for the exam. Okay? These are ideas that I happen to know are on the exam. I know it in my gut. Okay? First of all, this idea of elastic, inelastic, maximally inelastic. Some of you are still trying to wrap your brain around those different types of collision. The most important thing you need to know is that momentum is conserved for all the flavors. There's not a collision in the universe that does not conserve momentum. Okay? That's just take it to the bank given. And it's not because we make some assumptions or massless strings. It just is. Okay? Now, maximally inelastic, you can see if they stick together, that's maximally inelastic. That's the definition. They stuck together, full stop, maximally inelastic. For these other two, elastic and inelastic, you can't see it. There's nothing that you can just look at and say, oh, that looks elastic, or sniff the air and, oh, that smells elastic. No, you got to do a calculation. You have to calculate the energy before the collision, calculate the energy after the collision. If you get the same number, it's elastic. If you get a different number, inelastic. Yes.
The kinetic energy or any kind,
What's that?
just the kinetic energy or any kind of mechanical energy?
Any kind of mechanical energy, but typically you're looking at collisions on a level surface such that mechanical energy is kinetic energy. Yep. Okay. Now, the basic collision problem, you're going to have to solve 4 times on the exam in different situations. Okay. So this is something that you should have in your toolbox ready to go. Okay. And this is the basic collision problem. I give you the masses and the velocities, and then after the collision, I give you one of the velocities and ask you for the other one. Or I could give you the 2 final velocities and not one of the initial ones and ask you to find that. Okay. The key here is that the total momentum of the system, comprised of everything that's colliding, has to stay the same. Now, if I look at the momentum of the red block, that's 4 times 8 or 32. And because it's going to the right, it's positive 32. For the blue block, that's 4 times 12 or 48, but it's negative 48 because it's going to the left. When I add those together, I get negative 16. That's what gets conserved. That's what stays the same. After the collision, regardless of how messy it is, I still have to have negative 16 Franci. And if I look at the red block, it's got negative 12. Well, if everyone's got to pony up and we got to come up with negative 16, the blue block has to have negative 4, right? And that means that the velocity here has to be 1/3 meter per second to the left, because 12 times 1/3 gives me 4, and because it's to the left, it's negative. Okay? Check your neighbor real quick. Can they do that? Can they do that? Maximally inelastic, they're not going the same speed, right? So it can't be that. They're not stuck together, right?
They stick together maximum.
Right.
Glad I'm paying attention in this class.
I would have to calculate 1/2 MB squared for that, plus 1/2 MB squared for that. Add them together, and then do the same after the collision. And if I get the same number, it's elastic.
Minus now 36.
My parents were down.
This way it's going.
Pound of fresh pine nuts.
Yeah, that can't happen. That's a mistake in the problem. Yeah. Was that in the homework problem? Oh,
Very strange. Like, is this on the max?
yeah, that can't happen. It'd have to pass right through it. I'll fix that. Okay, folks. There's another way I can ask this question. I can say, what if they stick together? Okay. Well, we didn't change anything about the original state of things. So that means that this is still going to be the same 32 to the right, and this is still going to be the same 48 to the left. So I'm still going to need a negative 16 for the whole system. But now, because they're moving together, I can treat them as one ugly block with mass 16 kilograms. And so if these have to have a momentum total of negative 16 Franci, that means they have to have a velocity of 1 meter per second, because 16 kilograms times 1 meter per second, 16. Okay? So you can do those types of problems as well. There are these types of problems that are going to appear each twice on the exam. And here's an example. A 500 kilogram car is moving at 20 meters per second when it hits its brakes. And we assume that it locks the brakes and it's scraping across the pavement. You can hear the scraping going on. Okay. We have two different questions we can ask about that. We can ask how far will it slide, and we can ask how many seconds will it slide for. Now, if we use our decision tree, the first thing we ask is this a collision? Well, no, it's not a collision. This is a scraping. And the second question is time involved? Well, it is over here, so that's going to be a momentum problem. If time's not involved and it's not a collision, that's an energy problem. So over here, I would use the energy equation. The energy in the morning is equal to the energy at night, except when it's not, and it's usually not. Now, in this case, by energy, we mean kinetic energy because it's a level road. And the vert done is being done by the friction force. And it's negative because the car's going one way and the friction is pushing the other way. Whenever the force and the displacement are opposite each other, that's negative vert. That bleeds energy out of the system. And so if I plug in everything I know, 1/2 mv squared gives me 100,000 joules. The friction force is 2,500 newtons. I solve for that and I get 40 meters. Again, those numbers are not important, folks. The process is what's important. That problem's not going to be on the exam with those numbers. You need to know the process. Okay? Now, if I'm looking for how many seconds it slides, that's a momentum problem. And here, it starts with a certain momentum. And then if I call this positive, I have defined a coordinate system. I have said the direction the car is going is the positive direction. And that means the friction has to be negative because it's fighting that motion. And so now if I plug in for the mass times the velocity, I get 10,000 franci. The friction's the same as before. The time is going to be 4 seconds. Okay. Now, if it travels, if it slides, if it scrapes 40 meters in 4 seconds, I take that 40 meters and I divide by 4 seconds, that gives me 10 meters per second. Does that make sense? That's the average speed. If it starts to slide at 20 meters per second and it ends it at stopped, the average is halfway in between, namely 10 meters per second. Okay? Now, that handout, if you turn it over, has a two-dimensional collision problem. There will be a two-dimensional collision problem on the exam. That problem has 5 parts, okay? And each part is worth 4 points. And so that is going to be worth 20 of the 100 points on the exam. So you need to be able to work these two-dimensional problems. So let's work this one real quick. Thank you, Sam. So the first part of this problem asks us for the total momentum, magnitude, and direction of the two-vehicle system just before the collision. Now, folks, I'm not speaking to all of you, but some of you. Some of you lost points on that last midterm because you were asked for vector quantities, magnitude, and direction, and you just gave the magnitude. You didn't bother to give the direction. And every time you made that mistake, you lost a point. Don't let that happen again, okay? If it's asking for the magnitude and direction, give both. Now, the most important step in one of these two-dimensional problems is drawing that vertical line separating the x part of the problem from the y part of the problem, where we're using a standard coordinate system like that. So if we call that a car and we call the other one an SUV, okay? No, it's a truck. I should have read. The car is traveling all in the x direction. None of its momentum is in the y direction. And I would get its momentum by multiplying the mass, 300, by the speed, 18 meters per second. And that gives me 54 hundred Franci. Does everyone see where I got the 5,400? 300 times 18. 300 times 18. The truck, on the other hand, has no momentum in the x direction. It's all in the y direction. And if I take the mass of 600 times the speed of 12 meters per second, I get 7,200 Franci. The total momentum for the system, I just add up the columns. 5,400 in the x direction, it's 7,200 in the y direction, both positive. Is that the total momentum of the system before or after the collision? Both. Both. That's what we mean by conservation. And what that looks like is an x part of 5,400, a y part of 7,200, and the total momentum is going to be this vector here. And that's going to be given by the square root, this Pythagorean theorem, 5,400 squared plus 7,200 squared. And that gives me 9,000 Franci. This angle is going to be the inverse tangent of the opposite side over the adjacent side. And that's going to give me 53 degrees. So I would say the total momentum of the system is 9,000 Franci. That's the magnitude, always a positive number. Magnitude's always positive. The direction would be at 53 degrees north of east. The most important word there is of. That direction is east. You're going to go north of east. 53 degrees. Now, part B is free points. Did I mispronounce 3? No, I meant to say free. It's asking you for the total momentum after the collision. Oh, it's the same. It's the same as what I had, 9,000. Every stinking time. There is not a collision in the universe where it's not true. Okay. Now to find the velocity, folks, I will post the solution to this problem at Max. We need to get to the devotional. Today we have the person that produced that wonderful hit series, The Chosen, speaking. Review session tomorrow night. Be there, be square.